Hi, welcome to the next video in this section. This section is a bit more advanced with wave shapes. That's why I've called it complex wave shapes. So let's get right into it. Okay, reasons for combining sounds. The first one's pretty obvious. You would combine sounds to create new original sounds. You can also combine sounds to make a weaker sound stronger, like I showed you in the other video by adding the sine wave underneath the saw wave to give it more bottom low end punch. And you can also use a combination of sounds to make a sound smoother. Now there's several ways to combine sounds as well. So two similar sounds can be doubled, which I shall show you in a second. And you can also layer two different sounds to create a unique sound, which will be shown later on in this video. First thing I'm going to show you is oscillators times 2. So two versions of the same oscillator, or doubling. Basically, doubling oscillators makes the sound louder if they're in the same phase and polarity, which I shall explain later also. But it also allows for more sonic opportunities. You've got two different oscillators. Sorry, you've got two different modules with the same oscillator. They can then be manipulated in such a way to give you more opportunities than just having the one waveform would have done. So I'm just going to go into Cubase now and open up Zebra 2 and give you some examples of this. Okay, so here we are with Zebra 2 version 2.5 using the unempty Dark Horse skin, which can be found up here. Basically what I've done is I've got one oscillator using sine tree, which can be found if you click in here. Got factory oscillators, sine tree, it's there. I'm just going to open up the Blue Cat oscilloscope also. So here we have the oscilloscope. I'll just show you how to set this oscilloscope up. It's very simple. You just go to routing. For instance, if I play a note at the moment, you can't see anything. You need to go to routing. Then in this I want channel 1 and channel 2, which is my main stereo out. Probably be the same for you guys. Click on routing again, so that goes away. And you can name it and stuff if you want to. And now if I press key, there we go. To magnify into that, see the little cross, all you need to do is left click and drag to a section, it will magnify in. Then magnify in again, until you get it where you want it to be. Okay, and if you want to put the 0 point crossing line up a bit, if you just come up here and click on the hand, you can just kind of slide it up to there. And then you've got what you're after. Okay, so doubling. We've got one oscillator here, one sine wave. There we go. Pretty self-explanatory. Now if I add another oscillator with the same sine wave and all the same settings, what will happen? Because they're on the same polarity and same phase, it will double the amplitude or the volume. That's how you'll perceive it. You can see there. So that's doubling at its most basic form. Now, as I mentioned, because we now have two oscillators, even though it's the same waveform, it gives us more creative opportunity than what would be available if we only used the one oscillator. Sure, we can certainly do things with this oscillator. We're not kind of messing with any of the phase or the effects or anything like that at the minute. We're just talking about the pure waves forms. So we could make it a bit wider, we could detune it with itself, add a bit of vibrato, which is great. But because we've got another oscillator, we can take that even further, even just by using those same parameters. So if we get the sine wave to play, and then perhaps maybe detune them from each other a little bit, add a bit of vibrato, you will start to hear some of the other sonic possibilities. Of course, we're using two sine waves, so the possibilities are limited by the fact that they're sine waves. However, it doesn't have to be sine waves. It's just easier to teach you this using sine waves. So here we go. So again, instantly we've got a different sound. And as you can see, the waveforms all over the place now. Of course, you can use the tuning. You can pan, so I could pan one far left, one far right. Some weird stuff going on there now. Some nice sub. Then we can detune them. So let's detune this one by 3 semitones. This one by -3 semitones, say. So as you can hear, there's a nice sound coming through now, which is much fuller and just a nicer sound all round than just the sine wave on its own. Now, of course, that's just 2 oscillators with 2 sine waves that have been slightly adapted. You can put filters in there, envelopes in there, do whatever you want, and of course you can use more complex waveforms. However, we'll get on to that. So let's move on. The next section in this video is related to what we call oscillator phase and polarity. Very easy to understand. We'll just read out what we've got down here for what they are. Phase. Phase equals the position of a wave's cycle. So if we take the red sine cycle here, so that's a 360-degree cycle. So phase, that's 0. That's 90 degrees in the cycle of the sine wave. That's 180 degrees, that's 270, and that's 360. Phase, very easy to understand. Polarity. Again, very easy to understand. It simply means whether the wave starts with a positive or negative cycle. Very simple. The red waveform goes up or into the positive part of the spectrum. So that has a positive polarity, whereas this orange one starts by going down, so it has a negative polarity. I'll go into this in more detail in a second, but it's very important to understand that. And again, really simple. And this dotted line here, see this dotted triangle line here? This is pretty much showing you a triangle wave that is starting at 108 degrees out of phase with a sine wave. So this triangle wave would be called 180 degrees out of phase with a positive polarity of this sine wave. Nice and easy to understand. Why do you need to know this? Let's get into that. Okay, so say we've got 2 waves with equal phase and polarity, which is exactly what we just did with the sine wave. So we'll go back to that. Okay, so here we are back with Zebra 2. And again, we have the 2 oscillators, both of which have the same waveform. They are both using the same phase and the same polarity, which means that you double the output volume, or whatever you want to call it, but amplitude, I guess, is really what it is. So you double the volume or the signal strength. So turn one off, turn the other one on, exactly the same phase and polarity. We double it. Now, if you notice on the oscillators here, we have a phase button. If we click on those, here we have the phase settings. Now, I know that both of these are in the same phase because the phase button is at 0. I know that they're in the same polarity because the invert button relates to polarity. Invert off means it's positive. Invert on, negative. Okay, so why do we need to know this? Simply, well, there's many reasons, but in this case I'm going to give you a simple reason. If you have 2 waveforms that are out of phase, this will result in cancellation. However, this is waveform dependent. Now, if I put the sine wave on oscillator 2 out of phase with the sine wave in oscillator 1, because they're sine waves and there's only the fundamental harmonic, they'll cancel each other out completely. So if you watch what I do. There we go. So because that's completely out of phase with oscillator 1, it's complete cancellation. However, if we were to try that with two saw waves, let's have a look at that. So I've got the two saw waves here, just the initial patch. Watch the oscillator, the oscilloscope. There is a certain amount of cancellation, as you can see, but it hasn't completely cancelled it out. And again, that's down to the relationship of the harmonics. So what's actually happening here? Let's go back to the diagram and I'll show you. So what we just done there was we had two sine waves that were playing using the same polarity and the same phase. However, we then moved the phase 180 degrees. So the first sine wave started here, and then when it got to here, the second sine wave started here on a positive polarity, so it went up the way. So if you imagine the second sine wave starting here, ignore this part of the orange one for a minute, starting here, so the orange one was going up, the bottom one was going down. So what in fact was happening was they were cancelling each other out. Positive and negative, they cancelled each other out. If it started here and followed like that, they reinforced, but because it started 180 degrees out, they cancelled each other out. So, as you can see, now if you imagine this carrying on down here and up here, and then that coming up here, basically like this, that will cancel each other out. Those cancel each other out. And as I've already shown you, two sine waves, 180 degrees out of phase, but same polarity, gives total cancellation. Okay, the next section. Some common controls that you will find and that are very helpful when using phase and polarity. Phase sync. What that means is every note from the oscillator will start from the same position in an oscillator's phase. So every time you press a key, the oscillator will start at the beginning of its cycle. So again, if I go back, so every time I push a key, it will start there, or wherever I've told it to start. It always starts at the beginning of its cycle. Let me just show you that. Okay, so here we have one oscillator with a sine wave, and as you can hear, it constantly starts at the same place. Now the control that's related to that is the reset button. That is directly related phase sync. Every note from the oscillator will start at the same position in the oscillator's phase. Okay, maybe it's better to use a saw wave to show you that. Just reset the oscillator. Okay, as you can hear with the saw wave, you'll hear it starting at different points in the cycle. Take a listen. If I put the reset button back on, you'll hear it jump back into control. So that's what the reset button does. It's directly related to phase sync. Next one you'd really need is phase control. You need to be able to control the phase of where the note begins. If you can't control the phase, then you can't put one wave out of phase in relation to another. Now that's pretty much what I just showed you earlier on using the phase button, but we can go back to that and hear it working. Okay, so we're back in Zebra. We've got two oscillators. They're both set to reset, so they both re-trigger at the beginning of the cycle. Now if we start to use the phase button, you'll hear this one start to trigger at different points. But by this, you can actually control where it starts. And in Zebra, by the way, 0, 180. So it's now 180 degrees out of phase with this one. 50 would be 90, and so on. Okay, the next one is polarity reverse, which I explained a little bit about earlier. You need to be able to reverse the polarity of a wave so that you can, well, have two waves at different polarities, so you can use them to cancel each other out a little bit. You can use that to reinforce a sound. It's pretty much what I showed you with the waveforms. So here, they are out of polarity. Positive, negative. Again, we can show you that in Zebra. So back in Zebra, we've got the two oscillators again. And let me just put that to saw bright, I guess, why not? So we have the two saws, and I'll invert one of them and just listen to what happens. It almost thins the sound out a bit because there's a bit of cancellation going on there, like I explained earlier. And then, of course, in conjunction, you can use the phase to create different textures. Now, it's almost like a bit of chorusing there. So as you can see, very useful. Okay, on to the next section. Okay, free running. This is essential. If you don't have this control, then your sounds will be static, especially things like pads. This allows the oscillator to start at any point in its cycle, adding variation and a touch of randomness. So what that basically means is, every time you push a key, again, it's going to be completely random as to where in the cycle the oscillator starts. So on Zebra, free running is turning the phase sync off. So if you just turn that off, it's now free running. It's a free running oscillator. Which allows for a bit of randomness and helps you to add variation when you're creating things like pads and stuff. And other stuff as well. Okay, let's move on to the next section. The next section is hard sync. This is a good diagram to explain this. Hard sync basically means that you slave one oscillator to another. So you have a master oscillator, which in this diagram would be the stick orange line. And your slave oscillator is this dotted line here. So what happens is, you push a note, the waveform then goes through its cycle, and then your second oscillator, when you use sync, is forced to start at the same time as the first oscillator. As you can see here, they're both out of phase. But here they're in phase, and here they're in phase. So when you push the first note, they're out of phase. The second time you push a note, the slave oscillator is forced into phase with the master. Now the slave oscillator, as it says here, the slave oscillator restarts its phase each time the master oscillator restarts. So each time you push a note, the slave oscillator restarts its phase. This can result in very hard sounds, great for leads. I'll just show you that. In Zebra, it's the sync button here that we're dealing with. So let's have a listen to Saw Wave on its own. We'll just put reset on so it's... Okay, now we'll turn the sync on, and you may be thinking, how's that working? There's not two oscillators on this, but these oscillators in Zebra can sync to themselves, and they do have multiple possibilities. If you come into mix, you can change. So if we change it to dual, we've now got two oscillators. Now if we go back to phase, we turn on the sync, you're not hearing anything yet. But if we bring it up, you'll hear it to start. The sound will become really cutting. So if you listen. But the great thing about these oscillators is you don't actually have to use dual. You can use single, and it slaves to itself if you like. So this is single. Now that's real. So as you can see, the hard sync is a great feature. Turn on two oscillators. use the sync on this. And then the sync on this one as well. Now you're getting a really cutting edge kind of lead. And of course, everything I've showed you so far is just with the oscillators. We haven't done, there's no filtering involved, there's no envelopes involved, there's certainly no effects, and we haven't detuned anything really, so you're getting these kind of sounds just messing around with two very basic saw waves and messing around with things like sync. Okay, let's move on. Okay, the next section I'd like to talk about is detuning oscillators. Now, Zebra's particularly good for this because of the type of oscillators it has, especially the multi-oscillators, which we'll get onto in a moment. But detuning, basically, subtle detuning can give a chorusing effect, which is great for adding fatness to a sound. But also, if you detune oscillators too much, it can result in the sound actually becoming out of tune, which I shall demonstrate now. Okay, here we've got one oscillator in Zebra. I'll turn the other one on. So we've now got two oscillators. I'll just reset the sync. So again, two oscillator sound. And now, using the detune button, we can detune them from each other. And what this allows us to do is spread the oscillators, the waveforms away from each other, which gives us this chorusing effect. Which is great for things like hoovers. And for those of you who don't know what a hoover is, I'm not referring to the things that you use to clean your carpet. It's actually a sound that was kind of made famous in, I guess, the late 80s, early 90s, with tracks like Dominator and James Brown is Dead, stuff like that. It's just a really wide saw. You will hear people say things like super saws. It's that kind of sound. Here it's very minimal at the moment, but we'll see if we can get somewhere close to it in a second. Okay, now as we put the detuning up, you can hear it. If I just put a little bit, that's almost like a chorus effect. But the further we turn it up, you'll start to hear the oscillators start to detune completely. There, you can hear them detuning. And if I detune this one, it's not really usable, that, but if you're just subtle with the detune, you can get some nice effects. So let's go let's detune that by, say, 5 semitones, and this one by -5 semitones. It's a nice sound. Okay, so that's detuning oscillators from each other. Okay, the next section I want to speak to you about is multi-oscillators. Now, you may think that's just what we looked at a moment ago. We had two oscillators. Yes, you're correct. 2 is multiple. However, that was multiple oscillator modules. When we talk about multi-oscillators in this fashion, we're talking about multiple waves from the one module, which Zebra is very, very good at. Okay, so again, here we've got Zebra. Now if we come to the mix section, we've got this section here. Okay, we have a single oscillator. If we come in here, we can change that to dual. And as you can see on the oscilloscope, it's pretty much the dual one at those settings is pretty much double the amplitude. Almost like doubling. But with the detune, we can then detune these two oscillators in the two waveforms in the one oscillator. So again, similar to what we just did with two oscillators, but we're doing it in one. So listen. And you can see the effect of them being detuned. They're slowly starting to move out of phase. And we can go further. But again, that's too much. So, but we also can take it further. We also have a quad setting. So now we've got 4 oscillators that we can detune from each other. It's a strong, strong signal now. And now we're starting to get a really full, lush sound. Again, it can be pushed too far, obviously. Again, depends what you're after. And believe it or not, it's got an 11 setting. So we now have 11 oscillators that we can detune. Some fantastic sounds. Again, just from one oscillator, and of course you can push it. And that's almost like a Hoover. It's not like the Hoovers of the 80s that were very different and very unique, but the principle's the same. Okay, so that's detuning multiple oscillators in one oscillator, or multiple waveforms. Oh no, sorry, yeah, multiple waveforms. So there's 11 oscillators in fact there, 11 saws at the moment. So let's move on to the next section. Sorry, just before we do move on to the next section, normally in multi-oscillators you'll have the following controls. Now, number of voices, number of oscillators, which was this section here. So voices or oscillators. The next one is detune, which again is relative. It's the relative detuning of the oscillator. So you're detuning the oscillators from each other, which is here, this knob here, when we were detuning it. And the last one's width. What this does is spreads out the multiple oscillators over the stereo field. So imagine far left, far right, it spreads them out. The more width, the more it spreads out. So let's listen, let's get a nice dual sound. Okay, now listen to what happens when I increase the width. You can hear it being pushed out in the stereo field, and you can actually see it on the oscilloscope as well. If you watch the oscilloscope, watch what happens when I increase the width. You'll see the waves really spreading. And of course, you use things like 11, you can get some crazy, crazy stuff going on. So, that's your multi-oscillator settings. Let's move on. Okay, this final section is just really something I wanted to add to kind of show you a few things can be achieved by adding different waveforms together. So, as it says here, you can add 2 different waves to create a third unique wave. Basically, this is reasons for combining waveforms, really. A common use is combining a wave 1 octave up or down from another wave to add high-end bite or low-end punch. And you can also combine waves, combining waves also helps you move away from only using subtractive synthesis. When you're getting into the realms of adding waves together, you're starting to use additive synthesis, which we will take a look at later on in this course. So, just some examples of that. Here we have a sine wave. When a sine wave and a sine wave pitched an octave higher than the first sine wave are combined, the result is a brand new waveform. So we've got a sine wave here, then we've added a sine wave 1 octave higher. We know that that sine wave's an octave higher because there's twice as many cycles in the same amount of time. And it gives you this kind of waveform here. Let's have a look at that. Okay, so here we have 2 oscillators, 2 sine waves. So what we're going to do is create oscillator 2 to be 1 octave higher than oscillator 1. So at the moment we've got this. 2 sine waves, exactly the same polarity, same phase as we've demonstrated earlier. Now I'm going to put this this sine wave 1 octave higher, and we use the tune button to do that. And if we just put that to 12, that's 12 semitones. Now look at the wave. Okay, so we've created a new unique wave. Okay, so the next one that we're going to look at is this. What we have here is a sawtooth and a square wave. When they're combined, the result looks like a combination of the two. Now you can see here we've got the square wave here, the square wave there. We've got the sawtooth section here. So it's, as you can see, it's got the sharpness of the sawtooth, but it's kind of got the shape of the square wave. So let's have a look at that. Okay, so I've changed oscillator 1 to init again. I'm just going to change oscillator 2 to the, where is it, pulse table. So that gives us a square wave. So if I turn oscillator 1 off, we get a square wave. So we've got a square wave there. Turn oscillator 1, oscillator 2 off, and we've got a saw wave. So now if we combine both of them, we should have something that looks kinda like both of them. There you go, that looks like a combination of both of them, yeah? We've got the square wave pattern, but it's got the sawtooth extremes at the higher ends of the positive and negative there. Okay, let's look at the next one. The next one is combining 2 saw waves together. One of the saw waves, this one, is 180 degrees out of phase with the other one. So if you remember where it's starting in the cycle, this one goes through 180 degrees, then this one starts. And what happens then is the result is a sawtooth which is 1 octave higher than the original sawtooth. So let's have a look at that. Okay, so here we have our 2 oscillators, 2 sawtooths, just the initial patch. Make sure reset's on, so 2 sawtooths will look like a sawtooth. There we go. So what we're going to do now is put oscillator 2 180 degrees out of phase with oscillator 1, which will then give us an oscillator 1 octave, or a waveform that's 1 octave higher than the original. So listen. And as you can see, there's twice as many cycles as what there is when they were in phase. So if you watch the difference, the amount of cycles that are in, well, 1 second, but just watch the amount of cycles. So, and of course you can hear that it's 1 octave higher. And I can prove that. If I bring this phase down, I will play 1 octave higher on the keyboard now. Now I'll play 1 octave lower on the keyboard but increase the phase, and it should sound like that. So there you go. So just watch. You see the time disappearing and it becoming, the cycle becoming longer. So let's move on to the next one. Okay, this one is again combining 2 saw waves, but this time we're going to combine one with its polarity reversed. So as you can see here, instead of going up, it comes down. And it's also 180 degrees out of phase with this one. And what we should get is a square wave. Now, if you use your imagination and take this and plant it over here, you can actually see where the square wave will come from, because that will kind of stay there. This section here will cancel out this section here, which gives us the square. But let's have a look at it in zebra. Okay, so again we've got our 2 saw waves, just the initial patches. This time we're going to invert the wave on oscillator 2, and we're going to put it out of phase by 180 degrees to try and create a saw wave. Now, here goes. As you can see, it's already been shortened. There's the square wave starting to appear. Okay, so it kind of looks like a saw wave there, doesn't it? Being 180 degrees out of phase. So let's just mess around with it a bit. And of course, these figures that I'm giving you, they're perfect world scenarios. So we don't know what kind of inconsistencies are going on in these oscillators that may not give us the perfect shape. But let's see how close we can get to it. That's kind of close. We've almost got a square wave there, haven't we? But it's got a few weird inconsistencies going on. Now this will probably be directly related to the type of saw wave that we're using here. It may not be a perfect saw wave. And of course it may just be some of the other algorithms involved in these oscillators. It's very, very difficult to get very, very perfect oscillators. But it's close. It's not too bad. I don't think we can get any closer than that. I think that's as good as we're going to get it. But you can see now that by combining different waveforms, you can create a whole host of interesting stuff. And of course, we've only discussed the 5 basic waveform types. The reason we look at these 5 basic wave types is because it kind of stems back from analog synthesis, where that was really the only type of waveforms that were available. But if you look, like for instance, if we look at this modern oscillator here, if we come in here, there's just so many different types of waveforms here. Like spectral smurf. You know, what's that? There's all kinds of things going on there. It looks like a sine wave actually that's got really kind of FM overtones, but I don't know what's going on there. But there's just so many choices nowadays. And another great thing about Zebra, one of the things that actually makes me love it, is this feature here. It's just incredible. What have we got here? We've got a triangle wave. We can then morph it into a saw wave, which then morphs into a pulse wave. And that can be controlled by an LFO. This kind of stuff here. So you can play waves that are constantly changing. And this is all part of the greatness of the digital domain. You couldn't do this in analog synthesizers when they were first available. And there may be some that can kind of offer stuff like this, I guess wavetable synthesis, things like that. But again, we covered the 5 basic ones. There's so many more options. And this is just one oscillator. One oscillator, you can have 11 playing. You can detune those. You can tune it. You can add effects. You can do loads and loads in Zebra just with one oscillator. That's why I find it so fantastic. But anyway, enough about me wobbling on about how fantastic Zebra is. I hope this video has been really useful for you. I hope you've gained some understanding over these 2 videos actually, basic waveforms and more complex waveforms, and I'm hoping it's kind of getting your juices flowing for getting into some more or being more adventurous with your synthesis. I shall see you in the next videos.